All right, one last video on function composition. So in the previous videos, we've learned how to do function composition. And I just made the argument that sometimes it's useful, I think I even wrote those words, to run these two machines back to back. But I never even talked about why you would ever want to do this. This might feel kind of strange. You might have kind of enjoyed it, maybe not, who knows. But I have never given you any justification for why it would make any sense in the world to create some big machine by kind of running two other machines back to back, by putting one machine sort of inside of another, informally speaking, like we've done in all these examples. So in this video, I want to teach you why. The answer for why is going to be kind of frustrating because it ends up being the answer for why do we do most things in a pre-calculus class. The short answer is calculus, right? In calculus, it turns out it's going to be really useful to decompose two different functions. For me to give you the answer to what you get when you build a big machine out of two different machines' parts, and for you to tell me what two machines did you put together in this strange way to create that machine in the first place. And that question is what's called function decomposition. And frankly, it's pretty hard, and it's probably beyond what we should be doing too much in this pre-calculus class. All I really have to do is kind of expose you to it. I want to show you what function decomposition is and kind of work through a couple of examples. But don't expect to get tested much on this, and don't expect it to show up a whole lot in the homework. I think there's a couple of problems at the end. Okay, the first comment that I want to make about function decomposition is it feels more like a puzzle. I'm not going to give you a series of steps that you can employ to solve these things, which can be either fun for a student or really frustrating for a student if it's the first few times you've done this. Really what I'm going to ask you to do is kind of see things. So maybe I'll kind of demonstrate it the first time, and it won't be at all obvious the first time, but maybe you can just focus more on understanding what I'm doing as opposed to thinking about whether you would be able to recreate those steps. And then we'll do a couple of examples and I'll show you how you can recreate those steps. So the idea here is we have this composite function, and if you can view it color-coded like this, then maybe you'll be able to figure out which two functions we compose together to create this composition in the first place. Because what you're doing with function composition is you're trying to identify what is the function g of x and what is the function f of x that, when you compose them together in this order, gives you this huge mess as the composite. And for me anyways, the easiest way to think about it is there's a function that's kind of on the inside here that goes into the other function. So what I'm doing here is I'm looking for a function that kind of exists inside this huge mess. This 10x minus 49 will be that function. Because the 10x minus 49 is on the inside, loosely speaking, and the g of x is the function that's on the inside here, my g of x is 10x minus 49. And then what I have to do is think about, okay, what was the function f of x that I put 10x minus 49 into to create this mess? Because if g of x is 10x minus 49, then this entire thing is what I would get if I changed all the x's in f of x into 10x minus 49. You're basically working backwards. The idea is there's some function up here, and when I change the x into a 10x 49, the first term looks like this. So the x must have been raised up to the fifth power. And in my second term, I subtracted something squared. That something ended up being the 10x minus 49, but if the input were just the letter x, it would have been minus x squared. And then I have this plus 3 out here. Decomposing functions is really hard, but the good news is composing functions isn't all that bad. If you struggle with this, you can always check your answer by just figuring out what would f of g of x be equal to here. Well, if I was evaluating f of g of x, I would start working from the inside out. I would say that g of x is 10x minus 49, at least I think it is. So what I'm going to do is replace g of x with 10x minus 49. And then what I have written here is f of 10x minus 49, which is just telling me to take this machine f of x and change all the x's into 10x minus 49s. So I would have something raised up to the fifth power minus something squared plus 3. And that something wouldn't be the letter x, it would be this input 10x minus 49. And then what I do is I stare at what I have written down here in green and make sure it's the same is what was given to me up here in black, and since it is, I know I decomposed these correctly. Wow, that's really hard. Let's try to do another example because maybe it's the kind of thing that we just need to learn through repetition. Here's another composite function, 7x plus 11 squared divided by 7x plus 10. You might think there's a typo in here. You might think it should say 7x plus 11 squared divided by 7x plus 11 or something like that. But actually it doesn't. The trick to this problem is to recognize that we could rewrite this as 7x plus 10 plus 1 more squared divided by 7x plus 10. 7x plus 11 is just 7x plus 10 plus 1 more. But if you rewrite it in this form, maybe you're at the point where you can recognize that there's a function on the inside here. It looks like the inner function is again g of x, nested inside some other function. Maybe you can look at this and color coordinate it in this way. And if you're able to color coordinate it in this way, maybe you can identify that the inside function g of x would be 7x plus 10, and the outside function f of x would be x plus 1 squared divided by x. And you're like, wait, why is it x plus 1 squared divided by x? Well, it's not obvious that that's the answer, but you can always compose them back together. We could figure out f of g of x. What we'd do is we'd work from the inside out, so we'd first change g of x into what it's equal to, 7x plus 10 in this case. And then what we'd do is we'd evaluate f of 7x plus 10. We'd copy this function f of x, which is x plus 1 squared divided by x, except instead of writing x as the input in all three of these spots, we'd write 7x plus 10 as the input in each of these spots. This expression simplifies. 7x plus 10 plus 1 more is 7x plus 11, and that's what's being squared up in the numerator. And in the denominator, I just have 7x plus 10, which is the same thing that was given to me in green over here. If you're feeling like these are really hard and you're feeling overwhelmed right now, you're not alone. That's kind of how this always feels when you first learn function composition. But we're not done with this video. Let me try a little bit more to teach you this stuff. If you're really clever, you might have noticed that this isn't the only way that we can decompose this into two different functions. I didn't have to make my inner function 7x plus 10. Another option would be to make my inner function 7x plus 11. And you're like, wait, how would that work? If I was making that my inner function, if these were both 7x plus 11s, how would I recover this function that I see written here? Well, the answer is we'd have to choose a different rule for f of x. Instead of being x plus 1 squared, in the numerator it would just be x squared, because I want the numerator to be 7x plus 11, what I have in red, squared. And you're like, right, but there's a problem. We want the denominator to be 7x plus 10, not 7x plus 11. So I can't just divide by x. I'd have to divide by 1 less than x. I'd have to divide by 7x plus 11 minus 1 more. The point that I'm trying to make is function decomposition is not unique. There's different ways that we can take this composition of two functions and decompose it into two different parts, which makes function decomposition so difficult. However, that's also good news that this is recognized to be super difficult, because the kind of questions that you'll see in our class won't look like this. I won't just give you some composite of two functions and say, decompose it. Because if I did that, your answers won't all match up. Some might give me this answer, some might give me this answer. So what we're going to do instead is I'm going to give you one of the two functions and you're going to give me the other one. So for example, suppose we had this composite, x plus 2 to the 5th power divided by the square root of x plus 2. And I told you that the inside function here, g of x, was x plus 2. If you knew g of x was x plus 2, could you figure out what f of x must be equal to? Well, maybe now it's a little bit more manageable, right? Because g of x is x plus 2, maybe it would help to rewrite this thing with g of x in red. And maybe when you color coordinate it like that, it's a little bit easier to see what the outside function f of x must be equal to. Informally speaking, f of x has to kind of capture this 5th power and this square root here. So f of x is going to be x to the 5th power divided by the square root of x. If that's hard to see, I got at least two options for you. The first one is, as we've seen in previous examples, checking the answer is always a good way to go. So because g of x is given to us to be x plus 2, and we want to figure out something that's equal to f of g of x, all I have to do is figure out what would be f of x plus 2 if my answer for f of x is x to the 5th divided by the square root of x. Well, let's see. I guess what I would do is I'd copy exactly what I see right here, except I'd change all of the x's, the input for this function, into x plus 2's, loosely speaking, the input for this function. So instead of x to the 5th power being divided by the square root of x, I would have x plus 2 to the 5th power being divided by the square root of x plus 2. Answer checks out. Looks like I did everything right. One last way to think about this that may or may not help you is we know that f of g of x is this expression right here. And since we're given the inside function g of x is x plus 2, we know that f of x plus 2 is equal to this expression. A minute ago, we saw that we could come up with this expression by changing all the x's in this expression into x plus 2's. But if we didn't already know this f of x, another way we could have come up with that answer is just by copying this line, but changing all three of these x plus 2's into x's. On the left side of the equation, instead of f of x plus 2, I'd then have f of x, exactly what I'm looking for here. And on the right side of the equation, changing this x plus 2 into this x, and changing this x plus 2 into this x, gives us the same value that we came up with earlier for f of x, the answer to this question. One last problem, then I'll call this video good. This example might look a lot like the one that you see above, where you're given a composite function, and you're told one of the two functions and asked to determine the other one. But what's different about this one than the one we just completed is in the one we just completed, we were told the inner function, g of x, and we're asked to figure out what f of x is equal to. In this example, we're told the outer function, f of x, and we're asked to determine what the inner function, g of x, is equal to. I think it's a little bit harder this way than it was on the easier one, but we can still get a pretty good idea of the answer by employing some kind of clever color coordination. This time it's the outer function, f of x, that's given to us, so the stuff in blue is supposed to be 2x squared plus 1. So I'll begin to write that. However, I'm not going to write the x in here. I'm just going to leave some open parentheses because the input for my function f here is not x. It's going to be some other function, g of x. So I'm sort of copying this blueprint right here where f of x equals 2x squared plus 1. But instead of writing the x's in this place, I'll write a g of x on one side of the equation, and on the other side of the equation, I'll just kind of leave it blank and fill that in later because what I fill in here will be the value for g of x, the answer to the question. If you can get to this setup, the answer is not too hard to come by. If you just go staring up here, the only thing that's missing, the only difference between this and what I have written over here is inside the parentheses over here, there's a 3x plus 5. So if I change the input for the f function into 3x plus 5, what that will give me is the composite function that I was given in this problem. Now maybe if you stare at this thing, the value of g of x is pretty obvious. G of x in red on the left side of the equation is equal to that 3x plus 5 that I just wrote on the right side of the equation. The answer to this question would be g of x must be 3x plus 5. Just like in the previous ones, if function decomposition gives you a hard time, you can always check your answer by composing the functions back together. F of g of x would be f of 3x plus 5, which is equal to copying this expression for f of x, 2 times something squared plus 1, but changing all the x's in this expression into this new input, 3x plus 5. When I do that composition, it looks like it gives me this composite function that I was given originally. Therefore, my decomposition must have been correct.